record this, shrink it. Now, a couple of things. Let's just talk about inverse trig functions for starters. In fact, let me maximize this page. Very important concept. Let's say the sine of 30 degrees equals 1/2. That means that the inverse sine of 1/2 equals 30 degrees. Okay? And what this means is that we're always taking trig functions of angles to come up with ratios, right? And we're always taking inverse trig functions of ratios to come up with angles. So that's a big starting point. Realize that when you take an inverse trig function, you're taking it of a number, or more typically a ratio of two numbers, and you're going to come up with an angle. In other words, if I wanted, I know you're familiar with the 3, 4, 5 right triangle, but nobody's probably ever told you what theta is right there, because it's not important. However, if you wanted to solve for theta, let's say somebody says, what's theta? The angle opposite the side 3. Well, I would take the inverse sine of 3/5. In other words, I'm going to take the inverse sine of that opposite over hypotenuse to come up with that angle. That angle turns out to be about 37 degrees. Okay. All right. Let's go back and deal with your problems. So what's the inverse sine of 1/2? Now, let me ask you something. This looks like an online, you have to fill in the answers online?
Yes.
You have it open so that you're going to fill them in as we do them?
Oh yeah, actually I didn't pull that up, but I can.
Okay. Or you could just write the answers on paper and then go back.
Yeah, I usually write everything down.
Okay. We can do it either way. Sometimes these are a little tricky, and that, boy, I really don't like these where you put answers in online. Because they're so picky about it.
Yeah.
You put the correct answer in, but if you don't put it in the exact method they want you to put it in, it tells you wrong, and then it's just a frustrating experience. So,
well, I have it up, so.
Okay. Well, it's good then. At least you'll be able to check, make sure that the answers we come up with are the ones that you want. So, to answer this first question, I need to know the sine of what angle is equal to 1/2. Always refer, when you're looking at problems where they do not expect you to use a calculator, and this is one of them, I'm sure, right? You're not allowed to use calculators here. Okay.
Right.
Well, the two triangles that you want to memorize are both right triangles. One's the 30-60 and the other's the 45-45. Okay. And beside, it's not so much the two triangles you want to memorize, it's what their dimensions are. Well, on the 30-60, I call these my unit triangles. So the side opposite the smallest angle is always 1. That makes that square root of 3 and that 2. So you really want to memorize these two triangles. This one over here is 1. Clearly that's 1. It's isosceles. And that's square root of 2. Kind of the basis of trig is these two triangles. In other words, they're never going to say what's the sine of 29 degrees without using your calculator. But any angles that are 30, 45, 60, or multiples of 30 or 45, they're going to expect you to know those by heart.
Right.
And you can always figure them out, okay? In other words, if I said to you, what's the sine of 60 degrees? What is it?
√3/2.
Okay. What's the sine of 30 degrees?
1/2.
So what's the answer to this problem?
The sine inverse. Oh, is it just 2?
No, we're looking for an angle. Remember that the
right.
sine
Okay.
gives you angles. Okay?
Oh, so it's 30?
Exactly. 30 degrees. But they want your answer in radians. Okay?
Right. Okay.
So here's something else I'd like you to take note of. And that is that pi over 2 equals 90. Pi over 3 equals 60. Pi over 4 equals 45. And pi over 6 equals 30. Notice what's in common with everything. The denominator times that is 180. 180. 180. 180. Okay? Makes for a quick method to switch between degrees and radians. In other words, I know that they've taught you there's a conversion factor. It's 180 over pi or pi over 180, depending on which way you're going. But that can be harder and more complicated. Notice how easy this converts. In other words, I know that 90 degrees is pi over 2 because 2 times 90 is 180. Okay? And now let's say they gave you a harder one. What is 2 pi over 3? Well, I could use the conversion factor, but notice it's much easier to use that. If pi over 3 is 60, what's 2 pi over 3?
120.
Yeah.
Okay.
And 4 pi over 3? In other words, the tough ones. What's 4 pi?
Oh, so it's 180. Okay.
No, it's 4 times the 60.
Oh, so 360.
And so,
Or 240.
in other words, yeah, all of these, the ones that everybody dreads seeing, you can do by this method over here, I think, much easier than using the full conversion factor.
Yeah, it's much simpler.
At a minimum, you want to know these 4. Okay? And our angle was 30 degrees. So what's the answer in radians?
It is pi over 6.
Go ahead and enter that. Let's make sure we've got enter. I don't know how you enter it. They give you a special table for where you just enter.
Yeah, they have all the functions and everything. Yes, it's correct.
Okay. Now, you'll notice something else. That if I took the sine of 150 degrees, I also get 1/2, positive 1/2. So one could say that the inverse sine of 1/2 is also equal to 150 degrees. And that wouldn't be wrong. But they call these inverse functions, they want to make sure they're functions. So they don't deal with the whole unit circle when you're figuring these out. For sine and tangent, if this number inside the argument is positive, you are in the first quadrant. If it is negative, you are in the fourth quadrant. for sine and tangent and their reciprocals. That's true. In other words, they don't give you the other quadrant that it's also true in. They just don't. Your calculator can only give you one answer. And if you put the inverse sine of 1/2 in, it'll give you 30 degrees. If you put the inverse sine of negative 1/2 in, it'll give you minus 30 degrees, which is a fourth quadrant angle. Okay? So bear that in mind. On all of these problems we're looking at, I don't actually see any negative arguments, so it might be immaterial to go through that. Now, let's look at B. Inverse cosine of square root of 2 over 2. Well, if you try to find square root of 2 over 2 in these two triangles, you can't find it, right? However, what would the cosine of 45 degrees be?
1 over root 2.
Which rationalizes to what?
Root 2 over 2.
Ah, there we go. So root 2 over 2 is the same as that. Okay, so what angle are they referring to?
45 degrees.
And radians?
Pi over 4.
Okay. Now, and that, go ahead and put that in. That's the answer. Now, cosine is slightly different than sine and tangent. If I have a negative argument on an inverse cosine, then that is second quadrant. In other words, if you put into your calculator inverse cosine of negative root 2 over 2, it gives you the second quadrant angle, because cosine is considered positive in the first but negative in the second. And so whenever they're dealing with a negative argument for an inverse cosine, it's second quadrant, as opposed to tangent and sine, which are fourth quadrant. Okay?
Okay.
I don't know if that's confusing or helpful to you.
Yeah, that makes sense.
I'm not sure we need it on any of these, because all of these have positive arguments, I believe. So what's the arctan? Same thing as inverse tan of root 3.
So tan is opposite over, so is it 60 degrees?
Okay, good. Put it in radians.
Pi over 3.
Good. And notice that that didn't have a 1 under it, but it really does. That's square root of 3 over 1. Because, like I said, trig functions are always ratios. Sometimes you have a 1 in the denominator, but they're always ratios. Okay, let's look at B. The inverse sine of root 2 over 2.
Okay, so that's just...
What angle is that? Always remember that you're looking
45, right?
Right, exactly. It's the same as the cosine.
Pi over 4, okay.
So pi over 4, exactly. All right. Now they get a little trickier. When you're taking the tan of the inverse tan, let's see if I can think of a little bit better one to do. I think I want to go through this method with you. Let's say we have the sine of the inverse tan of 1. Okay, and they want to know what that is without a calculator. Well, you could do it the hard way. And the hard way is to start from the inside and work your way out. Okay. Well, what's the inverse tan of 1?
40, or
Correct. 45 degrees.
40,
Okay. And now what's the sine of 45 degrees?
pi over 4.
No, when you're taking the trig function of an angle, you're going to get a ratio. Let's hold that straight.
Right.
So make sure when you're taking trig functions, you end up with ratios. When you're taking inverse trig functions, you end up with angles. I don't want to use the word number. I'm using the word angle, even though angles can be written in numbers. When you use radians, a radian is actually a number. But very important concept with trig to differentiate between the ratios and the angles. Okay, so what's the sine of 45 degrees?
1.
Look at that triangle that we had. 45, 45 triangle. What's the sine of 45 degrees?
Oh, the sine. Sorry, I was thinking. Oh, so 1 or root 2 over 2.
Correct. Okay, so that's the hard way to do it. Let me show you the better way to do this problem. I can solve this without ever knowing what angle is. Let's just make sure that we know that that inverse tan of 1 is some angle. We don't necessarily have to know what it is, okay?
Mm-hmm.
In fact, I'm going to solve this problem without figuring out what theta is. And that's what you're supposed to do. First step, draw a right triangle and label theta. And know that theta is this angle right here. Okay? Now, can you dimension any part of that triangle? If we know the tangent of that is 1, then what has to be true?
Both sides have to be 1.
Well, that has to be 1, and that has to be 1, because the tangent is opposite over adjacent. Okay? Now, we've labeled two sides of this triangle. I can use the Pythagorean Theorem to label this side, square root of 2. Now, I can take the sine of theta from the triangle. Sine of theta is 1 over square root of 2. I solved that without ever figuring out what theta was. That's really the way you want to do all of these. Whenever you have a trig function of an inverse trig function, you want to do it this way. And because sometimes, what if that was 3/7? Okay? Now, notice that is, oh boy. If I make that 3/7 instead of 1, well, that's not going to be one of my 30, 60, or 45, 45 triangles.
Right.
So if I didn't have a calculator, I would have no idea how to figure out what theta is. But I'm writing theta there to impress upon you the fact that what is inside the parentheses is an angle. Okay?
Mm-hmm.
Now, if I draw my triangle, just any right triangle, very key part, label theta, because theta could be this angle on the lower right, or it could be this upper angle. So make sure you label theta. Now, dimension the triangle as well as you can.
Okay, so... Oh, so the opposite is 3, and then the adjacent is 7.
Good. Now that always allows you to figure out the third side using the Pythagorean Theorem. So you want to get good at using the Pythagorean Theorem, I guess. I don't know. This trig they're giving you here looks preliminary to the calculus of trig. And in the calculus of trig, you don't have to do this exercise very much. But clearly they want you to know how to do these problems.
Mm-hmm.
What is the hypotenuse?
So it's the square root of 58.
It's the square root of the square of the sum of the sides. So you're right. Square root of 9 plus 49. Okay? And for the moment, I don't really care if that can be simplified or not. As it turns out, it can't be. 4 doesn't divide into that evenly. 9 doesn't. 16 doesn't, and so forth. So that's the dimensions of my triangle. Now, what's the sine of theta?
So then it's 3 over root 58.
Yeah.
And then,
Okay. You know what? I'm going to leave the rationalizing to you.
Yeah.
A few teachers here in Denver that tell their students, don't bother rationalizing any of this.
Yeah. My teacher isn't that strict about that.
Well, and there's a reason for that. Because what would the cosecant of theta be?
It would be 58 over 3,
Right.
or root 58.
Right, and that's why they don't much care about rationalizing it. Because if I had to go to all the trouble to rationalize that, I would get 3 root 58 over 58. And now I can't really simplify that, so that would be my answer. But now if somebody says, what's the cosecant of theta? Well, now you got to reverse it again. You got to put 58 over 3 root 58, and then you got to rationalize that again. So when you rationalize early, you frequently just make extra work for yourself. Okay? So I love the philosophy of don't rationalize, don't worry about rationalizing. Okay? Simplifying, different story, but that can't be simplified. So a tough problem like this, notice once again that we didn't figure out what theta was at any point in time. We figured out what the sine of theta was, but we didn't figure out what theta is. And that's the way these are meant to be done. They don't want you necessarily to figure out what theta is to answer these questions. Now, we get to one where it says the tangents of the inverse tangents, and I'm going to write it like this, of 1. Well, a lot of people know that the answer is 1. In other words, if you take the tangent of the inverse tangent of the argument, it's usually the argument is the answer. But not always. And in fact, in the very next one where they have the inverse sine of the sine, the answer is not 7 pi over 3. So you can't automatically assume that the answer is going to be this argument. Okay? So if we do this the same way we did the others, I'm drawing a triangle. First of all, I'm going to label that theta. Very important that you know you're dealing with the tangent of an angle that's called theta. Okay? And I'm going to label theta on my right triangle. And now I know that, well, that has to be 1 and that has to be 1, right? Okay? And then I'm going to figure out that's square root of 2. And now, well, what's the tangent of theta? 1 over 1. So the answer is 1. So doing it my standard way also gives you the correct answer. You can take a shortcut on some of these and just know that the answer is 1. But be careful of that shortcut if there's unusual things. If there's negative signs anywhere, might make that answer different. Okay, so go ahead and put 1 in for A. Now hold on a second, let me think for a minute. Yeah, that's an angle. You're taking the tangent of the angle, so you're going to get 1.
Yeah, that's correct.
Okay, now the next one. The inverse sine of the sine of 7 pi over 3. Well, if we were using the simple logic, you might say, well, the answer's got to be 7 pi over 3. And that actually is not wrong, but it's not the answer they're looking for here. You always want the answer to be first quadrant or fourth quadrant.
Mm-hmm.
Well, let's convert 7 pi over 3 into an angle that's in the unit circle. That's outside the unit circle. Notice that that's greater than 2 pi.
Right.
So
So you
subtract
have to subtract,
as many
right?
multiples of 2 pi as you can, still leaving a positive angle. What do you get?
Is it 60 if I subtract 360? Or is that too much? Or you do it at...
Just subtract 2 pi.
Okay.
2
So,
pi is 6 pi over 3. So 7
right.
pi over 3 minus 6 pi over 3 gives you...
Are we going... wait, sorry. I don't remember the unit circle that well.
7 pi over 3 minus 2 pi. Well, I'm going to change the 2 pi into 6 pi over 3, so I have a common denominator.
Right.
Now 7 pi over 3 minus 6 pi over 3 is 1 pi over 3. So pi over 3 is the same as 7 pi over 3.
Okay.
Okay? So really, my problem, there's a software bug in this stupid program I'm using. I know it's not my tablet, because if I use a different program, I can erase just fine, but this won't let me erase. It does it in slow motion, kind of. Okay? Now, this is a little different. Notice that this is not the trig function of an inverse trig function. This is an inverse trig function of a trig function. So I'm not going to use my triangle problem here. I'm going to figure out, well, what's the sine of pi over 3? First of all, know that pi over 3 is what angle?
60.
Okay, so what's the sine of 60?
Is it... Oh, sorry. Okay.
Always refer back to
root 3
triangle.
over 2.
That's why
okay.
those two triangles are so important. You
Right.
absolutely want to be able to create those two triangles from your memory, not by looking at it on a piece of paper.
Right.
That's never a good way to memorize stuff, incidentally. Whenever you're trying to memorize something, don't have it on a piece of paper in front of you where you constantly can refer to it. It's not going to get memorized by osmosis. It really doesn't.
Right.
The best way to memorize stuff is go ahead and put it on your piece of paper, but then turn the piece of paper over and see if you know it. And then if you're not sure, check. But always be drilling your brain into trying to memorize that. Okay? That's why I don't always leave it on the page here. I don't want you to just look at the triangle and figure it out. I want you to be able to draw from your memory to figure it out. So the sine of 60 degrees again is what?
Root 3 over 2.
Okay. I can cross that out. And now, what's the inverse sine of root 3 over 2? If the sine of 60 degrees is root 3 over 2, then the inverse sine of root 3 over 2 has to be
2 over root 3.
No, 60 degrees.
Oh, okay.
Let's go back. I can't stress this hard enough. This is an if and only if problem. If the sine of this angle 30 degrees is 1/2, that means the inverse sine of 1/2 is 30 degrees. These two things are basically equal. So if you're ever trying to figure out inverse, know that you're looking for an angle, and if you're looking for an angle, it means the sine of whatever angle I'm looking for has to be 1/2. So you can find the inverse sine of 1/2 as long as you know the sine of 30 degrees is 1/2. With me?
Okay. Mm-hmm.
Okay. Hold on a second. Still getting used to my problem here. Yeah. All right. So the answer on B then is what? What?
Pi over 3.
Exactly. And they didn't say put it in radians, but looks like everything else they did request radians. So I would put it in as pi over 3.
Yeah, that's correct.
Okay. And notice we couldn't use the little trick of just whatever this argument is, that's the answer. Although in a way it is, it's just that 7 pi over 3 is outside the unit circle. They want your answer to be a first quadrant angle. Okay?
Right, okay.
All right. Now we get to the tougher ones. This is tangent of the sine, and it's just x. So this is similar to what I've shown you, where you draw the triangle and you label theta. So what's the first step here?
So we'll look at sine of x.
Not yet. No, the first step is always to make that theta.
Oh.
In other words, inverse sine of x is some angle. So I'm going to draw theta underneath it to represent it. I won't cross it out. In other words, I could run a line through inverse sine of x and say, well, we're going to call that theta. Okay. What's the next step?
Draw the triangle with theta.
What's the next step?
Then label, right?
Correct. So what can you dimension on that triangle?
So is it basically x over 1? So then it would be...
So that's x. That's 1. Now we got to figure out the other side. You always use the Pythagorean theorem here because you're always having to figure out that other side. So a really good skill for these kind of problems is the ability to solve a right triangle quickly. That's always a good ability in math. In other words, you don't always want to have to go back to c squared equals a squared plus b squared. It's very cumbersome to have to manipulate that algebraically to figure out the short side. The short side is always the square root of the hypotenuse squared minus the other short side squared. So if I were you, I would memorize this when you're trying to solve a right triangle so that you can do it instantly. By instantly, I mean relatively instantly.
Yeah.
Okay, so what's the answer?
So it's 1 minus x squared.
So first of all, whenever you're solving for a side of a right triangle, it's always the square root of something.
Right, that's what I meant. The root of 1 minus x squared.
Root of 1 minus x squared. Okay. So now we have our triangle dimension. Now what's the tangent of theta?
So tangent is opposite over adjacent, so it's the root of 1 minus x squared.
Hold on.
Or I mean x over 1 minus x, the root of 1 minus x squared.
That cannot be simplified. So that's your answer.
Okay.
So it's x over square root of 1 minus x squared. Go ahead and put that in there.
All right.
the next problem, number 5, is just the reverse of that. But we're going to solve it exactly the same. Okay? Sine of n. In other words, whenever you're taking the trig function of an inverse trig function, you want to use this technique. It's a beautiful technique because you can always answer it without knowing what the angle is. So what's the first step?
Make that theta.
Okay, so I'm going to call that theta. Second step?
Draw the triangle and label.
And label theta. Notice I could label this theta. It wouldn't matter a bit.
Mm-hmm.
I'm still going to dimension the triangle according to where theta is. So you don't have to label theta in the lower right. It won't change the answer. Okay, but just to be consistent, I'll label that theta. Now, dimension this triangle as much as you can based on that being theta.
So opposite is x and adjacent is 1.
Okay, now figure out the hypotenuse.
And then the hypotenuse is x squared plus 1, or 1 plus x squared.
Square root of that, yes.
Yeah, square root, sorry, I keep saying that.
I generally teach my students that when you're solving right triangle, just always start your answer with square root of. It's always square root of. It might be the square root of 25, which would simplify to 5. Just it's easier if you always remember that start your answer with square root of, and then you'll never forget it. Because it's easy to forget. You've forgotten it in the last 2 problems here. So it's a really easy thing to forget. So just always make sure it's square root. If it turns into a number, fine, but usually it doesn't, you know. Now, what's the sine of theta?
X over the root of x squared plus 1.
Put that in. That's your answer.
And it's correct.
I find it a bit surprising that they didn't give you any negative arguments for any of the inverse trig functions.
I know, it might be coming because this is our first.
Well, okay. Those are harder because then you have to determine what quadrant theta is in. In other words, every problem we've done so far, theta is a first quadrant angle. It's because the argument of the inverse trig function is positive. So theta always is going to be a first quadrant angle if that's a positive number. If that's a negative number, then this is going to become a fourth quadrant angle. And then you're going to be taking the sine of a fourth quadrant angle. So when you took the sine of it, you better come up with negative because you're in the fourth quadrant. So it gets a little tougher when you have negative arguments. All right. But on to trig. First of all, memorizing these inverse trig functions. Let's start with the easiest one. The inverse trig function of x. If that's y, what's y prime?
Is it
1
x
over 1 plus x squared. Notice something else. When we take derivatives of inverse trig functions, we do not get trig functions as answers. We get polynomials. Interesting, right? Because if you take the derivative of a trig function, you get a trig function. Right? You undoubtedly wouldn't be doing this if you hadn't already had derivatives of trig functions. Derivative of sine is cosine. Derivative of tangent is secant squared. The derivative of secant is secant tangent. So derivatives of trig functions are trig functions. but derivatives of inverse trig functions are always polynomials. Okay? There's three that you really want to memorize. There's tangent, there's inverse sine. Inverse sine is, I'll go ahead and give them to you, but trust me, you want to memorize these. That's what y prime is, if y is inverse sine of x. And the third one is y is inverse secant x. And that's the hardest one to memorize of all, because it's a little stranger than the others. First of all, it's x squared minus 1, not 1 minus x squared. Second of all, there's an absolute value of x right there. Okay? With me so far?
Yes.
Now, there's three other inverse trig functions. There's cotangent, there's cosine, and there's cosecant. In other words, what we listed were the trig functions, and the other three are the cofunctions of these three trig functions. Cotangent's the cofunction of tangent, cosine's the cofunction of sine, and cosecant is the cofunction of secant. Well, when you take the derivatives of those cofunctions, you just get the negative. So if y is cotangent of x, then y prime is negative 1 over 1 plus x squared. In other words, the derivatives of the cofunctions are merely the negatives, much like trig.
Okay.
By that, I'm not sure you're aware of this, but I'm going to make you aware of it because it's very helpful. If y is sine of x, y prime is cosine of x. Well, if I look at the cofunction, which is cosine, then the derivative of cosine has to be negative sine.
Right.
And let me just take it one step further, because this helps a lot when you're trying to memorize stuff. If you only have to memorize 3 things, it's much easier than memorizing 6 things. Wouldn't you agree?
Yes.
Well, if y is the cofunction, which is cotangent, then I know that the derivative is the negative of the cofunction. It's the negative of secant's cofunction, which is cosecant squared. And finally, the third one would be the derivative if the function is secant of x, its derivative has to be minus, first of all. What's the cofunction of secant x? No, excuse me, hold on, I didn't finish that. If the derivative of secant x is secant x tangent x, then the derivative let me screw it up here. I'm trying to put this in an orderly format so it gives you a nice way of memorizing, a much easier way of memorizing these. So if I'm looking at the cofunction of secant, which is cosecant, and I want to know what the derivative of cosecant is, as long as I know what the cofunctions of each of these are, I've got my answer. In other words, it has to be, first of all, minus, and it's cosecant times cotangent. So notice that the derivatives of I'm going to call these primary. Even though math doesn't call them primary, I'm distinguishing between the ones that have a co in front and the ones that don't.
Mm-hmm.
I'm saying my primary trig functions don't have the co in front. Whereas, in other words, you have to memorize these three. That's it. You don't need to memorize these three over here. You know that the answer to the cosine, first of all, is negative. There's a negative there, a negative there, and a negative there. So when you take the derivatives of the cofunctions of your primaries, you know the answer has to be a negative. And the trig function is the cofunction of this. In other words, sine x is the cofunction of cosine x. So when I'm taking the derivative of tangent, I know that that's secant squared, so the derivative of cotangent has to be negative, and that has to be the cofunction of secant squared. So if you've memorized the column on the left, you can always figure out column on the right.
Mm-hmm.
No, you got to figure out why this doesn't work. All right. I'm going to have to use a different drawing program, which I have, at least I used to have. And the same principle applies to inverse trig function. In other words, let's go back. If y equals inverse sine of x, what's y prime?
Y prime is
1 over something. All of these.
right. Okay. And 1 over the root of 1 minus x squared.
Good. Try to memorize that. So now if I said to you, well, now I have inverse cosine of x, what is y prime going to be?
Is it?
Just the negative of that.
Oh, okay.
The derivative of the cofunctions inverse cofunction, is the same as the primary function, only it's negative.
Right, okay.
So these are really easy to remember. So this is minus 1 over the square root of 1 minus x squared.
Okay.
So again, the only ones you have to remember are the inverse sine, the inverse tangent, and the inverse secant. The three that do not have the words CO in front of their name.
Okay.
Okay? All right. Let's keep going because I want to get through all of these. So what's y prime in number 6?
So is it 1 over, let's see, what do we do with the 7?
You can essentially take that out and leave it all alone until you're done. And then bring it back in, and it goes right there.
Okay.
Okay, so that's the answer.
Okay.
All right, now let's take a harder one. If I have y equals the inverse sine, and it's not x, let's say it's 3x, well, now I have to apply the chain rule. The best way to think of the chain rule is with U substitution. Are you familiar with that concept, U substitution?
Yeah, kind of. I'm not very good at it.
So in this case, I'm going to let U equal what?
3x.
Okay. Now when I take y prime, it's no longer a function of x, it's a function of u, which means I'm going to have to use the chain rule. So the answer, y prime, is going to be 1, over square root of 1 minus u squared, but then I've got to multiply it by u prime. And so when you have a more complicated function that's not just the inverse of x, but the inverse of something that's complicated argument, you have to you do exactly the same thing, but then you have to multiply it by the derivative of the inside. What's the derivative of the inside? We can figure that out over here. dy dx equals 3.
Right, okay.
So what's the answer?
For
this one?
Just, I get 3 over the root of 1 minus u squared.
But what is u squared? We need to give our answer.
Oh, it's 9?
X.
Oh, wait, 9x, okay.
9x squared, exactly.
9x
U squared is, because we set that up, u squared is 9x squared.
Okay.
There's your answer. Can't simplify it. Okay, that's my answer to this problem. I'm merely trying to illustrate the use of the chain rule when you're doing inverse trig functions. Okay, well, let's use it on the next problem. So we have y equals 5. Again, you don't need to do much with the 5. Just make sure that it's brought in at the end. What's u?
2x squared.
This is, yes, excuse me. What's u prime? Because we know we're going to need that.
U prime is 4x.
All right, so here's what our problem is. We have the 5 inverse sine of u, right? Okay. Well, we know our answer, y prime, has to be not 1 over square root of 1 minus u squared, but u prime over square root of 1 minus u squared. So what is that?
So it is 4x over the root of 1 minus,
Now,
and then
once
4x to the 4th.
you want to get rid of the u. In other words, we use u substitution in doing the problem, but then we always resubstitute back.
Okay, okay.
So what's that squared? What's u squared?
Then, oh, it's 4x to the 4th.
Yeah. And again, that's your answer.
Okay.
Oh, hold on. Forgot to bring the 5 back in.
Oh, okay.
20, 20x.
20, okay.
It's one of the problems with just totally ignoring that number is you got to make sure you bring it back in when you get your answer. Because that number you can't just ignore.
Right.
So 20x over the square root of 1 minus 4x to the 4th.
Okay. Okay, perfect.
And tell me when to go on. Make sure that that's what it says.
Yeah, that's correct.
All right. Another problem where we don't have just x. We have 4x cubed. So y equals 3, which we don't have to concern ourselves with yet. What's u equal to?
U is 4x cubed.
What's u prime? Because we know we're going to need it. Whenever it's a composite function and you're using u substitution, you know you're always going to need to multiply everything by u prime.
Okay. Yeah, it's 12x squared.
Okay. And then again, remember what inverse tan is? It's the simple one. It's 1 over 1 plus x squared.
Right.
So y prime, instead of 1, I'm always putting u prime in the numerator. because I'm always going to multiply this thing by u prime, and when you multiply 1 over 1 plus u squared by u prime, you get u prime over 1 plus u squared. Okay? So in my calculus book, when I look what the derivative of inverse tan is, this is always the answer it gives me. It doesn't give me 1 over. It just assumes that you're going to be having to use a composite.
Right. Okay.
Okay? So if u is just x, then that's 1. In other words, the derivative of x is 1. So you can always remember it's this, and then if u happens to just be x, u prime is 1. Okay?
Okay.
So what's y prime? And this time, let's not forget that 3.
Right. It's 36x squared over 1 plus 16x to the, is it the 6 or the, do you add it or?
Well, x cubed times x cubed. If I'm doing multiplication,
Okay. Right.
I'm always adding. If I'm doing division, I'm subtracting exponents. If I'm doing double exponentiation, then I'm multiplying exponents.
Okay.
But this is straightforward. Just when you square a variable to an exponent, you basically double the exponent. And there's your answer.
Okay, perfect.
Okay? Now, like to do 9. Actually, I don't mind going over a little bit here in order to get all these done.
Okay, if that's okay with you.
Yeah, it's fine. Let's see, we got 9 and 11, neither of which are tough. But number 9, I meant 10 and 11. Let's do 10 and 11 first, and then we'll go back and do 9. Just because 9 is a double application of the chain rule. In other words, there's 2 different chain rules required for number 9. Number 10, not so much. Would you? We'll do these fast.
Okay, so u is 2x plus 1.
What's u
and then
prime?
U is just 2.
So if y is that function, what is y prime?
Prime is 2 over the root of 1 minus is it 4 or 2x squared?
What's u squared? If u is 2x plus 1,
Oh,
what is
4. Okay, so it's 4x squared.
No. Here. Down here. 2x plus 1 times 2x plus 1. What do you get?
Oh.
That's what 2x plus 1 squared means.
Oh, okay, okay.
So
Oh, right, I was looking at u prime.
You got to FOIL these.
Okay, so it's 4x plus 2, right?
4x squared
4x squared.
plus 2x plus another 2x, so plus 4x plus 1. That's u squared.
Okay.
So in parentheses, and the parentheses are vital here because it will matter if I didn't use parentheses. There's your answer.
Okay.
You get your answer, make sure there's no u's left. In other words, you always got to put it back into x's. Now, your program here probably is not adept enough to accept multiple answers, but let's remove the parentheses and simplify that denominator because we can do that.
Okay.
Right?
Mm-hmm.
So 2 over the square root of what?
Over
First of all, remove the parentheses. So that becomes 1 minus what? What's the rest of it if I take out the parentheses?
Minus, is it 4x squared plus 4x
No.
plus 1? So is it just
Negative
4x squared?
sign has to apply to all three terms. So when I remove the parentheses, that becomes minus 4x minus 1. That's why the parentheses are so important there, because without it, you got a different answer. Now, that can be simplified. What does that simplify to? Certainly the 1 minus 1 goes away. So it becomes minus 4x squared minus 4x.
Okay.
Okay, and that could be an answer. However, I can factor out a 4. And then once I factor out a 4 from inside, I can take it outside of the square root sign. So this now becomes, now I'm seeing why this isn't as easy as I thought it was, why it was after number 9. I'm beginning to see why now, because they want you to simplify these. They always want you to simplify it down. Okay, well, here's the first step. I'm going to take a 4 out, leaving that, correct? Now I can take that 4 completely out as a 2.
Right, okay.
That. And now the 2's cancel, and you end up with 1 over the square root of minus x squared minus x. And don't think I can do anything more to simplify that. Go ahead and put that in as an answer and make sure that it's right.
All right.
These are tricks you want to kind of look for. In other words, if you ever have something inside the radical sign that looks like it could be simplified like we just did, in other words, if you're looking at some perfect square numbers in both terms, then I can certainly factor a 4 out, and once I've factored it out, I can remove it from the radical sign as a 2.
Right. And it's correct.
Okay. Go to 11, or we do the really tough one, although this could be pretty tough too. What's u?
U is x plus the root of 1 plus x squared.
What's u prime?
And then u prime.
We're going to need that. In other words, whenever you see a complicated argument that's going to have to be represented by u, you always need u prime.
So then is it 1 plus the root of 2x?
You got to take the derivative of that. And to take the derivative of it, rewrite it without the radical sign.
Oh, so
1 plus x squared to the 1/2 power, right?
Oh, right. Okay. So it's 1 plus.
Derivative of it is 1/2.
Okay.
1 plus x squared to the negative 1/2. But then I got to take the derivative of the inside, which is 2x. Right?
Okay. Yeah.
Are you good with the chain rule on just derivatives and polynomials in general?
I need to definitely work on it.
Well, the chain is basically no different than this. You're always taking the complicated part, turning it into u, differentiating u. And that's pretty much what the chain rule says, is that you take the derivative of the outside times the derivative of the inside. Well, the derivative of the inside is u prime.
Okay.
Okay, so u prime.
Right, okay. So this is like a multiple chain.
Yeah, exactly. Okay. Well, not really. There was only one chain rule involved in this problem.
Right, but more than one.
Derivative of the inside. So now, notice those 2's cancel. I have an x in the numerator, and I have this in the denominator. to the 1/2 power. So I'll write it like this, without the radical sign for the moment. So that's what u prime is.
Okay.
Okay. Now, let's go back and figure out what y prime is. What's the derivative of inverse tan? That's the easiest one to remember.
1 over 1 plus x squared.
Good. Or in this case,
Or u prime.
u prime over 1 plus u squared.
Squared. Okay.
Okay. So let's fill in the blanks. U prime is this whole thing,
Right.
which I will leave as that for the moment. Let's get the hard part. Plus 1 plus u squared. So we got to square that whole thing.
Right.
This is going to give us an extremely complicated answer that will then have to be simplified.
Mm-hmm.
Well, let me blow it up a little bit and see if we can come up with the answer on this. So let's see. Let's figure out what u squared is first. In other words, it's not a bad idea to always figure these things out before you even tackle the main problem.
Right.
We know we're going to need a u prime, and we know we're going to need a u squared.
Mm-hmm.
So what's u squared? You got to FOIL these two things together.
So it's x squared plus x root 1 plus x squared, and then plus x root 1 plus x squared, and then
that squared is just that thing without the radical sign, right?
right.
So 1 plus x squared. Okay, and now we can simplify that a little bit. U squared is equal to what?
Is x squared plus
Well, what's x squared
2x?
plus an x squared? I got 2x squareds over there.
Oh, 2x squared. Oh, right, I forgot that one.
Take
Okay.
care of that
2x
term
squared
and that term, plus 2x
plus 2.
square root of 1 minus x squared.
Oh, wait, where did the minus come from?
Plus 1, excuse me.
Plus, okay.
I usually cross the stuff out until I've crossed everything out, and I didn't look and see that there was still a plus 1 at the end of that. So that's what u squared is.
Okay. Oh, wait, is inside the radical plus, or is it minus? Isn't it root 1 plus x squared?
Okay, here's what we're doing. We're doing x plus 2x multiplied by same thing, x plus 2x root 1 minus x squared. Okay? Here's something really worth knowing. A plus b squared is always a squared plus 2ab plus b squared. So whenever I'm squaring a complicated term like this, I would rather use this, where a is x and b is this. Get me? So my answer is a squared, which is x squared, plus 2, you're right, I left off a 2, plus 2 times a times b. Well, that would be 4 a times b is 2, excuse me, should have done it like this in the first place, then I would have got it wrong. Let's see, so 2 times this times that is 4x squared multiplied by that. That's the middle term. That's this term right here. With me?
Right, but I'm just confused, isn't inside the radical, is it 1 plus or minus x squared? Because you says it's root of 1 plus x squared. That's just why I'm confused.
It's 1 plus, isn't it? What was the original problem? You know, I don't blame your confusion. It's 1.
Yeah, it's 1 plus x squared.
1 plus, okay. So this is plus, doesn't change much. So now that becomes plus there. So this is what u squared is.
Okay, yeah.
Okay? Yeah, let me cross off everything else up here. Let's see, did I get the third term? That's the middle term. That's not u squared. That's the middle term. And finally, the last term is b squared. And b is square root of 1 plus x squared. So that squared is just 1 plus x squared.
Okay.
Okay. And so we still have 2x squareds. And we have this plus 1. And that's actually what u squared is. I can't do much with that. I can't factor anything out because there's this 1 on the end. And let me think for a moment. Yeah, okay. So now we've got u prime over 1 plus u squared. Now let me write that. U prime is this divided by 1 plus this. Okay? 1 plus that. So let's see if I can write that, and then we'll figure out if we can simplify it. So u prime's in top. 1 plus x over square root of 1 plus x squared. That's the numerator. That's u prime. Divided by the denominator, which is 1 plus 2x squared plus 4x squared root 1 plus x squared plus 1. That's what y prime is before simplification.
All right.
Now, can we simplify that? Well, I can certainly combine the 1's in the bottom, so that goes away. Make that 2. Then I can actually factor a 2. Let's see what the top becomes when I combine these. In other words, when on the top I'm going to make a common denominator of this, which means I've got, there's my 1 plus x. So that's my new numerator after I combine the fractions. My new denominator is 2 plus 2. Now let's factor out the 2. Maybe it'll help. Because I got a 2 there, a 2 there, and a 4 there. So that leaves 1 plus x squared plus 2x times 1 plus x squared. Now, I can put this denominator as a multiplier in my real denominator. So I can change this. In other words, this is the same as flip and multiply.
Okay.
So now I got this over this.
Okay.
Now, let's see, I got a square root of 1 plus x squared here, and I got all of that times that is going to turn into 1 plus x squared, and I'm going to be able to do lots of simplification, I believe. Remember, when you take the square root of x times the square root of x, you get x. So if I got the square root of 1 plus x squared multiplied by that, it's going to turn into 1 plus x squared. But I also have to multiply this by the number, by this x squared, and by that 2x. So there's lots of simplification that can be done here. Unfortunately, it's probably going to take us a half an hour or 20 minutes to figure out how to do it all.
I think that I can enter it like that.
Well, I'd be surprised. I don't.
Okay.
You might. You could try entering it like this. In other words, this is your numerator, and this is basically your denominator. Make sure that that is multiplied by everything else. But the thing is that I know one simplification for sure is I'm going to be able to multiply this radical by this radical over here and have it get rid of that radical. But the other two terms end up with radical. So, and they're all simplifications, and then who knows what I'll end up with. Maybe I'll end up with something that looks exactly like the numerator, and I can cancel it all out. So a lot of times simplification can go a long ways towards reducing the complexity of the answer. Did you try putting it in?
Yeah, I'm typing it in right now.
Yeah, I don't think it's going to accept it as the right answer. But who knows, maybe. And this 2 in the denominator you could place in front if you want, as long as you use parentheses to denote multiplication is taking place for all three terms.
All right, let's see. Yeah, it's not.
No, I didn't think it would.
Yeah.
Rather than spending 20 minutes trying to simplify this and doing basically algebra only, let's go back and look at number 9. Because before I leave you today, I want to show you how to do double chain rule.
Okay.
Now, whenever you're applying the chain rule twice, I obviously can't let everything equal u, right? I'm going to let one thing be u and another unknown be v, just for understanding's sake. Okay? So the first u is going to be everything in the outside parenthesis. So what is u equal to?
Just, is it tan?
Inverse tan.
Inverse tan squared?
6x. That's u. Okay, and that's how I can say that this y equals u squared.
Okay.
Okay.
Oh, I understand. Yeah.
Now let's figure out u prime. You know we're going to need that.
All right. So that's what do we do with the tan again?
Well, it would normally be 1 over 1 plus x squared.
Oh, okay.
But
So
there's another inside. 6x is inside. So u prime is going to be the derivative of the inside, which is 6, over 1 plus the quantity 6x squared, which is 36x squared. So that's
Okay.
prime. Okay? So y prime is 2u times u prime. Based strictly on that. In other words, y prime, if this is not x, and I'm trying to find dy dx, well, u better be a function of x. And it is. U is a function of x. So the very first thing we need to do is take the derivative of the outside, which is 2 times u to the 1. And that's how I got that.
Right, okay.
Now I have to multiply it by the derivative of the inside, and that is that. Okay? So y prime becomes, I'll leave it in u for a moment, u times 6 over 1 plus 36x squared. But then we got to go back in, substitute for u. Well, u is this. So it's 2 times inverse tan of 6x all times that.
Okay.
And that is 12 inverse tan minus, hold on, one. Let's see, that's, hold on, I got lost. Let's see, let me go back here. Sorry. U is inverse tan of 6x, so 2u is 2 of those. And I'm multiplying it all by this. That's the way, in other words, I'm multiplying this times this. And I end up with 12 inverse tan of 6x all over 1 plus 36x squared. That cannot be simplified. Go ahead and enter that in.
Okay. Yeah, it's correct.
Good. So we got all of them but 11, huh?
Yeah, I'll work on 11.
And 11 is just a lot of hard algebra. Notice that, let me go back to 11 for a second. Whoops. Nah, can't even do it. Let's see. Oh. I don't know how this program, oh goodness, it's going so far back, I can't find what I was. But that's probably a good place to stop.
Yeah, I have it all written down too.
Work on it, or you can always access the video of this. I'm recording it. It'll be posted by tomorrow morning.
Okay. Wait, and how do I access the videos again? Do I have like
I've
a website with...
I sent you a link a couple times if you want to search through it, but the easiest way is go to YouTube and go to my channel. My channel is Digital Math Tutor. So if you were to type www.youtube.com youtube.com/digitalmathtutor, you should go to my channel, and then what you're looking for is your initials, Morgan Harrison, and the date. So today would be 030117. So that's the file you're going to want to see. Okay, and you still there, Morgan? Lost audio somehow.